So in the previous part, we optimized our optimized neighbor script, and most of the part was optimized. So the most expensive function is our hash set dot contains, and currently everything is working perfectly fine. So this is how our project looking right now, and there are not any issues anywhere, but we could have saved some space somewhere. So let's see where we could have saved the space. So as you can see, currently it is uh, so as you can see, this was not supposed to happen, as if we have such position, then the only position this could be filled was directly going through it, and all the empty positions are just going to be invalid. So just adding more checks, and what it will do, it is going to reduce the branching factor. So in the previous part we had 200,000 solutions for the 4x4 grid, and now it is going to be reduced further. So let's create a new folder, and what are the changes? Okay, so let's create a new folder and transfer all of our generate methods. Why am I creating a new script? So there are, let's create a new folder, and this is going to have all of our generate methods, and it is going to include our optimized neighbors and everything, and it is going to reload, and we are going to create a new script, and we'll call this branch reduction. And this script is going to start similarly as our vector to point script. So let's open up the script in Visual Studio, and it is going to completely be similar to our vector to point script. So let's first have a namespace. So it is going to be for our connect dot generator dot branch reduction, and it is going to inherit all of the classes, and we are going to have some minor changes. So there are going to similarly be our grid list comparer and our data class, and the script is going to be completely similar to our vector to point, so we'll also copy that, and everything should be working perfectly fine. So let's go inside Visual Studio, and we should have saved everything. So what we are going to do is first add our branch reduction script, and we are going to add the counter and solutions, and it also needs to implement the generate method interface. So let's go inside Visual Studio, and as you can see, it is not implementing the generate method interface, so it won't be able to get the component. And even if we have created the method here, the null the get component will return null, and there will be a null reference exception, and now there shouldn't be any. And let's go inside Visual Studio, not Visual Studio, Unity, and let's see if currently our script is working fine. So as you can see, it is checking all the solutions, and if we increase the speed to 30,000, it is going to check for all the 200,000 solutions. So as you can see, it is fast, and we are going almost at the speed of 10,000 per second, and in around 20 seconds it is going to go through all the nodes. And what we are going to do is reduce the search space. So at the start, when we created our all neighbor script, the search space was 9,000, and after we just divided by it, cause you already know, like it is going to be similar. So there is some, okay, so it is 1, so it was for 0. So let's go to 0 and it is going to stop at around 180,000. So as you can see, it is again going at the speed of 10,000. And what we need to do is just check if it is having similar count, and it should not be perfectly equal because we are using hash sets, and every time it may like produce some different result, or it may not, but there may be some collisions. So it found all the 180,000 solutions, and now what we are going to do is further reduce those solutions. And what solutions we need to reduce is let's check our this 5 cross 5 script. So as you can see, there are some stupid solutions. So suppose why did this happen here? So it may have started from here or here, the empty position, but the starting condition can only be from this row. And if it even would have occurred here, so if it start from here, if there is an empty cell that cannot be filled, then it should return false. And what it should have done is like if it goes like L shape here, then what it should do is all the succeeding neighbors and all the empty positions, they should be cleared. So the branching factor overall is going to reduce, and I don't know how much time is going to happen, but it is going to reduce substantially. So previously we have 9,000 solutions, and for our 3 cross 3 grid, the final is going to be around 150 solutions, 150 counts, and the total number of solutions are only going to be 3. So let's go inside Visual Studio, and what we are going to do is instead of having empty position, we are just going to have empty positions, and we'll need to create new list, and we are going to set that list. So the first is going to be list of point, and another is going to be a list of point, and we'll call this empty positions. And am I recording? Yeah, so I already tried recording 3 times, but I forgot to change. So we'll delete this here. So neighbors are also going to be similar. The checking is going to be done inside our grid data class, and here instead of our neighbors, so the color ID is going to remain same. There are not any changes, but instead of empty position, we are just going to call neighbor. And similarly here we are just going to use the neighbor and our neighbor, and that's it. And what we are going to do is create a method to set up this neighbors. So it is going to be item dot get results list, and we'll pass our neighbors and our empty positions, and we'll need to create this method in our item. And what it is going to do, get similar empty position flow length, yeah. So public void get results list, and here we are going to pass a list of point, and the first is going to be our neighbors, and second list of point is going to be our empty positions. So now there are not any errors, and the checking direction is declared but is never used. So and we are not going to use the empty position, so we'll delete that method. uh, our flow length is going to have one reference. Is not neighbor is also going to have a reference. Currently it doesn't have, but it is going to have soon. And everything else is going to remain same. Now how our neighbors and empty positions are going to calculated is, first we are going to have 2D grid, which is going to store the number of surrounding empty positions, and it is going to store the surrounding empty positions for each of the empty positions. So suppose if it is empty and it just everything is filled around, so it is going to have the 0 degree of freedom. And if it has 4 degree of freedom, that means there are 4 empty cells surrounding it. So let's see how we are going to do it. So let's first create a 2D grid, and we are going to call this empty grid, and it is going to be a new int, and we are going to pass the level size, and after that we are going to set this grid for int level size, and what we are going to set it to is -1 value. And after setting at -1 value, we are going to loop through the grid again, and we are going to check if our current grid is empty. So is equals to -1, then we'll set its value to 0, and after that for int k less than 0 direction checks dot length, let's first create our temporary point, and it is going to be new point of direction checks of k dot x plus I, comma direction checks of k dot y plus j. So this is going to be a temporary point, and if is inside grid temporary point, and our grid at temporary point dot x and temporary point dot y is -1, so that means it is empty. And if it is empty, then we are going to increase the degree of freedom. So if none of them are empty, then it is going to return 0, and depending on how many positions are empty, it is going to increase. And after that we are going to create a list of point, and the first one is going to be our 0 neighbors, new list of point, and our all neighbors. So list of point so these are the 0 and all neighbors. So how we are going to calculate is for int I is equals to 0, I less than direction check dot length point, let's create temporary point, and it's going to be current position plus direction checks of I, and if is inside grid, our temporary point, and our temporary point is not neighbor, and our empty grid at temporary point dot x and y is not equal to -1. That means it is empty and it has some degree of freedom. So if our empty grid at temp point dot x and temp point dot y is equals to 0, then that means it is a 0 degree neighbor, and we are going to update our grid, and we'll update it to -1 because we don't want to add it again. So this is how the neighbors are going to be calculated, and after we have calculated the neighbors, we are going to calculate all the empty positions, and here again we are going to have three types of lists. So the first one is going to be 0 empty, and it is going to be new list of point. And if there are any 0 empty positions, then they are never going to be filled, cause the minimum flow length needs to be 3. And next we are going to have a list of point which are going to be 1 empty. And what is going to happen with 1 empty is they are going to be prioritized first, because they are always going to be at the end point, and we can always create a new flow there. And all the rest are going to be not mattered, which are the 2 degree and 3 degree flows, and it will reduce our branching factor. So so let's create a for loop to loop through all the neighbors. And what we are going to do is check if empty grid at I and j is 0, then that means it is a 0 empty. And if it is 1, then that means it is a 1 empty. And finally, if our empty grid at I and j is not equal to -1, then that means there is some degree there, so it may be 2, 3, 4. But if it is not -1, then it is guaranteed that it is going to be an empty point, and we need to add it. And after we have all three of our lists, so if our 0 empty dot count is greater than 0, or our 0 neighbors dot count is greater than 1, so both of them are going to be remain unfulfilled and will return. And after that, if our 0 neighbor dot count is equals to 1, then we are going to add neighbors dot add 0 neighbors of 0, and we are going to return. So it needs to be filled, and we are not going to add anything. And after that, we need to add all the neighboring points. So for each and item in our all neighbors, we need to add neighbors dot add item, and that's how all our neighbors are going to be 3. And if our flow length is less than 3, then we are going to return. And if it is not 3, then we are going to check if 1 empty dot count is greater than 0, then that means that is going to be the only grid that is going to be added, and it is going to be 1 empty, and it is going to be added to the empty positions. And after that, we are going to return. And if it is not, that means we need to add everything. So let's add for each, and here this is going to be all empty, and it is going to be added to our empty positions. And that should be it, and currently we are not having any errors, so let's see how it is going to work. So we coded everything up, and we'll check with our -1. And what it should do is reduce our branching factor to 146. And if we increase the speed more, so let's just use a speed of 3200, and if we go to our 4 cross 4 grid, as you can see, it is go through only around 20,000 nodes, or maybe even less. So as you can see, the total number of nodes decreased by a factor of 10. So as you can see, this method is pretty good. And to find all the solutions, we didn't have to check much and to see if everything works perfectly fine. So let's add a 16,000 and let's hit play. So the total number of solutions were 206, and again the total number of solutions found are 206. And let's see how all the solutions look. And we can also do this for our 1 cross 1 5 cross 5 grid, so it is also going to show us the solutions. And this method is pretty good. So as you can see, it is sequentially finding all the solutions. And what we need to have is we need to find all the solutions randomly. So every time we search, we are going to get a unique grid instead of some copies. And as you can see, again, it is working perfectly fine. And I think it works good for grid of any size. So we reduce the branching factor, and if we go through 2 cross 2 grid, so let's see how it works. So it gave us a grid solution, and instead of 8,000, let's use 1600, and we are going to go through the 3 cross 3 grid. Let's hit simulate. So 1600 3200, and if we add some delay, then there will be not any issues. So as you can see, it just created a long grid first, and then it is going to fill with every possible solution. And again, it is not the best way, but it is all of them are going to be solutions. So it is not checking for any duplicates, so it works fine. But I don't know when is this ever going to end. So it checks for neighbors first, so that's why there is this issue, or we'll have some randomness. And yeah, so 3200, let's check if it works fine for 7 cross 7, and we are going through only, so still it is slow. Let's decrease the speed to 160. And as you can see, it is finding all the solutions, and if we have it choose the neighbors and empty positions randomly, then this would not happen, and that's what we are going to do in the next part. So instead of using a list, we are going to use a graph. So graph is going to just have the O of n square space instead of exponential, so we would be able to save some space there. And we are always finding a solution every 1000 or 2000 steps, so we don't need to check for the dictionary, so that's one issue. And we can remove the dictionary in the final part. In the next part, I'm not going to remove the dictionary because the solutions need to be same for the 3 cross 3 grid. And finally, when we are going to create the solutions for our 5 cross 5 grid, we are going to remove the dictionaries. So that is only going to be the last step. So as you can see, it has created some new grids and whatnot. So that was for this part. And what we did was further reduce the branching factor. So previously it would not have been possible to reduce, so let's go to the -1. And as you can see, there are only 146 search space, and if we go to the 0 and if we use 30,000, the search space is going to be decreased further. So the overall search space has been reduced by 10 times. And mm, so the main point is we are not going to go through some false solutions more and more, and we will eventually hit a solution and we'll hit it faster. So that was it for this part, and see you guys in the next one. So in the previous part we reduced the branching factor, and for our 4x4 grid it was reduced 10 times. And it is going to be factored more as the grid size increases. And the main advantage we have, it is it will not go through false solution more. So if there is an empty position, then it is going to directly just discard all of the uh, branches, so we won't search there. So in this part, as we are talking about branches and how our linked list was working, so it was almost stupid way to code all of this. And as we were using caching, so the caching was taking up almost 2 to the exponential space. And for now we are going to need caching, but what we have used is created a graph. And what graph is efficient, and we don't need to store anything, so we created a linked list to store the next one. So what we can do is we create a graph in which we just store all the neighbors, and whenever we want to check, we are going to just create a new node based off it. And the maximum number of nodes we are going to have is for 10 cross 10 grid is going to be 100. And as you can see, previously there were like millions of nodes and we were checking here and then. And the time taken is going to be remain the same, and we could have modified that. But the space in which it is taken is going to be just remain 100. So if we don't use hash set, so hash set saves all of it. So again, the spacing for hash set is going to be of exponential. And so let's first go inside our scripts, and we are going to create our final script for this part, which is going to be our graph random. So our graph random is going to be similar to our branch reduction script. So let's have a new namespace, and it is going to be connect.generator.graph random. And we need to switch to Visual Studio. So this is our new script, and we called it graph random. First let's copy our whole script, which should be up till our add to grid set. And after that we are going to copy all of our classes, so it is going to be till the end. And after we have done that, let's hide it here. Let's go inside Unity, and instead of branch reduction we are going to use graph random. And I haven't created anything still right now, so our script should work perfectly fine. And yeah, So there are 22,000 solutions. So let's me first create a commit. So this is going to be for our branch reduction commit. And branch reduce, and we are going to commit to graph random, and we'll push the origin. So it is going to get updated. So I just updated the current version to get, and we created our new script. And what we need to do is let's remove our branch reduction script. So 32,000.005, and we are going to add the counter and the solutions, and it also needs to implement the generate method interface. So let's go inside Visual Studio, and it's just one word, but if you don't check, then maybe if you are just forgot and happens. So let's go inside Unity, and what it should do is there won't be any more problems. So as you can see, it is again going to search through all 22,000 files, search space, and now we are going to modify our script. So we are going to go to Visual Studio, and what we are going to modify is we'll need to create a new data type first, so which is going to be of our grid node class. So let's create that class first, cause there won't be any problems afterwards. So if we are just creating a class, we just need to check for any typing error. So this is going to be our grid node class, and what it is going to have is a public grid node, and here instead of next we are going to have previous, and after that we are going to have a grid data, and it is going to be our data. And next we are going to have a private int. Am I recording? Yeah. So we are going to have private integer for our neighbor index and our empty index, and we are going to have a private list for our point, and it is going to be our neighbors and our empty positions. And after that we'll need a constructor, so public grid node, and here we are going to pass the level size, and what we are going to do is first we'll set the previous to null, and we'll set the data to be a new grid data of level size, and we'll need to create a new constructor, and our neighbors are going to be a new list of point, and our empty positions are also going to be a new list of point, and also neighbor index is going to be 0, and our empty index is going to be 0, and we'll need to add all of the neighbors. So for int I is equals to 0, I less than level size, for int j is equals to 0, j less than level size, empty positions dot add. So these are going to be all our empty positions, and we'll need to create a new constructor. So it is going to be inside our grid data class. So let's create grid data, and here we are just going to pass the level size, and what it is going to do is first set up our new grid and new int of our level size, and let's, after setting our grid, we'll use a for loop and we'll set our grids I and j to be equal to -1, and sort is going to be false, and color id is going to be -1, and finally our level size is going to be equal to level size. So that is going to be the constructor, nothing too complicated. And that was for the initial constructor, and after we are going to have our default constructor, which is going to so public grid node, and here we are going to pass a grid node, and it is going to be previous, let's call it grid data, and grid node previous, and by default our previous is going to be null, and what we'll do is data is equals to data, and our previous is going to be equal to previous, our neighbor index is going to be equal to 0, our empty index is going to be equal to 0, our neighbors is going to be equal to new list of point, and our empty positions are going to be equal to new list of point. And after that we'll get the result list and pass our neighbors and the empty positions, and we are going to shuffle. So we'll need to create the function, and we'll pass our neighbors, and again we'll call the shuffle function, and we'll pass our empty positions. So let's create our shuffle function. So public static shuffle of t, and what we are going to do is we are going to pass a list of point, and we will just call it list, public static void, and system dot random number generator is going to be system dot random, and after that int n is going to be list dot count while n is greater than 1. What we are going to do is decrease n, and we'll set the k to be rng.next of n plus 1, and where value is going to be equal to list of k is going to be equal to list of n, and list of n is going to be equal to value. So it is just going to shuffle randomly, and that's how we are going to create a new node. And we are not using our neighbor index and empty index anywhere, but we are going to use it. So where we are going to use it is to get a new node. So, and we'll call this next, and what it is going to return is grid data temp grid, and we'll set it to null at start, and we are going to return our temporary grid. And first, if our neighbor index is less than neighbors.count and our empty index is less than empty positions.count, then we are going to do a random. So unity engine dot random dot range from 0 till grid data dot level size, and we'll check if it is not equal to 0, then we are going to choose a neighbor. So temp grid is going to be new grid data, and here we are going to pass neighbors of neighbors of neighbor index dot x, neighbors of neighbor index dot y, and data dot color id, and finally the copy is going to be our data. So it is going to create a new grid, will increase the neighbor index, and we are going to return a new grid node, and we are going to pass our temporary grid and this, else will copy the same line. And here what we are going to do is empty positions of empty index, and similarly empty positions of empty index, and the count is going to be increased to 1, and here empty index is going to be increased to 1. And next we are going to check if our neighbor index, okay, so both of them are not true, that means only one of them is true. So if our neighbor index is less than neighbors.count, then again we are going to do the similar thing here, and again we are going to check if our empty index is less than empty positions.count, then again we are going to do the similar thing. And if none of this is true, then we are going to return null. So that is how our grid node class is going to look. And let's go inside Unity and let's see if we had any compilation errors. So there are not any issues, and all the 22,000 solutions, there should not be any problem. So again, the total number of solutions are similar. So we just created our grid node class, and instead of having like just a next, we are going to have the next and the previous. The previous is going to point to the previous node, and whenever we want to call the next, it is going to go to the next neighbor, and till it found all of the neighbors, and when it ends we are going to go to the previous. So let's play one more time and let's see how it looks. So we are just going to, so as you can see, it is also pretty much optimized, but we need to randomize the uh, point which is taking into consideration. So if there are multiple empty positions, then it should take a random position instead of the first one or the next one. So that's why we shuffled the list when we created. And in the next part we are going to learn how to use our grid node to iterate through all of our solutions. So let's end here. So in this part we are going to use our grid node which we have created in our previous part. So instead of iterating with our linked list, we are going to iterate through our grid node. So let's do that. So first we'll need to create a starting node which is going to be our private, and we'll call this grid node, and we are just going to have a current node. So private grid node, and we'll call this current node, and we are not going to need anything else right now, and after that everything else is going to be similar. And so all the methods are going to be completely different. So let's first set our current node to be a new grid node, and we are going to pass our instance dot level size. So this is our starting node, and our current node is going to be current node dot next. So we got to the starting part, and we need to set our checking grid to be our new grid list of our current node dot data. So what it is going to do is first we created a new node which had the previous set to null, and it had the starting color of -1, so it is just one dummy node which has no neighbors, and the empty positions are all of the positions in our grid. And what we did was then we go to the next node which is going to be any of the random position, and now our starting color is going to be 0, and after our starting color is 0 we set our checking grid, and what we do is we'll add to grid set our checking grid, and we are going to start the coroutine which is going to be our solve paths. So this is not going to be needed, and not showing the result, so nothing is going to be changed here, but there are going to be multiple things that are going to be changed. So grid list, we don't need the result grid list, we also don't need the item, and we are going to need the temporary list, and we are not going to need the connect list. We are going to need a new grid node, and we'll call this next node. And what we are going to do is while our current node is not equal to null, then our so the whole method is going to change, and current iteration is equals to 0, sol list is equals to sol list dot next, sol list dot next is equals to temporary list item dot is solved. Yeah, so let's first delete everything. We are going to need to create everything from scratch. So first thing we are going to do is get our next node. So this is our next node, and if our next node is not equal to null, that means we have some node, then we'll create a temporary list which is going to be new grid list of our next node dot data. And if not grid set dot contains our temporary list, then we are going to add to grid set our temporary list, and our current node will be set to our next node. Else our current node is going to be our previous node, which is current node dot previous. And if current node is equals to null, then we are just going to return, which is the yield break. Else what we'll do is we'll set the temporary list to be is equals to here, yeah, new grid list, and we need to pass our current node dot data. And if our next node is equals to null, then again similar thing. So current node is going to be set to the previous, and everything else is going to be similar. And after it has happened, our sol list dot next is going to be equal to our temporary list, and our sol list is our sol list dot next. And yeah, so as you can see, everything almost just simplified. So there were anything too complicated. And we can delete our direction checks, so no issues found. And that's how we are going to use it. And let's go to Unity and let's see if it shows us any errors. So as you can see, it is working similarly how it was done previously. So we checked, we added 125 grids, and it went through 250 times, and here it almost went through double the amount of time. So why the count is higher? Because sometimes it may have moved back, and also that is going to be counted as one step. And as you can see, the implementation was easier, but the grid node class was much more complicated how it was going to be implemented. And if I had known this at the start, then I would have created as it is done right now. But we learn when we create something. So the current code looks pretty much more better. And the grid list is going to be needed because we are going to simulate everything, or else everything is going to be working similarly with our grid node class. And whenever we found a solution and already shown it, we can just free up that memory, so that could save us some memory. But there is still one more problem. So let's see. So again, this is working perfectly fine, but let me show you for some larger solutions. So we need to decrease the speed, and let's have it only show 400 solutions at a time. And what is going to happen is it didn't happen here. Okay, so again it found a solution. Let's just increase to 7. So this is going to be our final level, and must be non-negative and less than the size of the collection. Okay, so so there was a problem with the color. We ran out of color. So what we can do is percentage it by our node colors dot count. and we are going to go inside Unity, and now it should not show any errors. So most of the time this problem is going to happen. So as you can see here, this is almost an impossible solution, and it should have ended right here, but we had no way to know like this is an empty solution, so that's why that was problematic, and it will be more problematic when the grid size increases. So we are not going to find it every time. So as you can see, this were two bubbles, and maybe it would have found a solution, but the overall checking space is still too much high. Until it reaches there, it would have grown to almost like billions of checking count, or maybe even more. So that is one problem. It is not bound to happen every time, but it will happen most of the time. So for any of the larger grids, so as you can see, it could have just discarded it here, and as you can see, it found a solution here, found a solution here, and this is never going to get solved. This also is never going to get solved, and that's why it is going to create problems later on. So it doesn't matter, as we are never going to go through grid size this large, and for our till 5 cross 5 the grid size is still pretty much small, so it will always get solved. So uh, any of the good grids are always getting solved in less than 1000 tries. So as you can see, it is always finding a solution. So we are not going to do that. We'll just find a new grid, and it is always going to work. So as you can see, it is this is also solved, this is also solved. It found a solution in less than 2000 tries. So it doesn't matter, we can just restart the loop again, and we can set a hard limit of 10,000 checks. So in less than 10,000 checks, all of our solutions are, any of the random solution is going to be found. Then if it is not found, then that means there is some problem. So as you can see, uh, there are so many of them which should have been checked, but it may create problems. So we'll need to fix that up, and I think we'll need to fix that. And that was it for this part. And uh, yeah, so to fix that, the main issue, yeah, so the main issue lies with our one empty. So when our one empty is there, then it is adding all of the different parts. So if we have two different sizes, where one empty pocket is just of size 2 and another empty pocket is of size 3, then what it should do is just check if the minimum pocket is solved, or will find the minimum pocket. So how we are going to do that is we'll create a set which is going to check for the minimum pocket size, and all of the solutions that needs to be found, they needs to be in the minimum pocket size, cause there are it is always going to be found first. So we'll create a new method which is going to store at a hash set. So let's create a hash set, and it is going to be of the point, and we'll call this min set, and it is going to be find min set min connected set, and we are going to pass a new list of point, and it is going to find the all empty and we'll need to create this method. So private static list point, and this is going to be get neighbors, and here we are going to pass a point. So so list point neighbor, result, and what we'll do is result dot add new point, and he'll pass point dot x, point dot y, plus will pass 1. After we are going to do result dot add new point, point dot x plus 1 and point dot y minus 1, and at the end we are going to return the result, and result dot add new point of control C, so collection initialization can be simplified. Yeah, so this is going to be a result, and we are going to return the result. And how we are going to find the minimum connected set? So it is going to return private, not private, public static. It is going to return a hash set of point, and we'll call this find min, and it is going to be connected set, and here we are going to have a list of point, and we'll call this points, and after that we are going to create first, which is going to be for our visited, and a list of hash set of point, and it is going to be our connected sets, and again it is going to be new hash set, and we'll loop through each of the point, and if our not visited dot contains our point, then we are going to create a new hash set, which is going to be our connected, and it is going to be new hash set of point, and our queue of point q is going to be new queue, and will q dot nq point, and while our q dot count is greater than 0, our point current is going to be q dot dq, and if our not visited dot contains current, then what we are going to do is we'll add to the current, and we'll add to the visited, so it is going to be connected, and what we'll do for each where neighbor in our get neighbors of our current, so for each of the neighbors we are going to check if not visited dot contains neighbor and points dot contains neighbor, so hash set of point all points equals to new hash set, and we are going to pass our points. So and all points dot contains point, then we are going to enqueue our neighbor. And yeah. Mm, mm, mm. So we could have used it somewhere. And after this queue count is finished, we are going to add our connected set dot add connected. And after our connected set, so hash set of point and main set is going to be equal to null, and for each item where item in our connected set, so for each item in our connected set, if our min set is equals to null, or our item dot count is less than our min set dot count, that means it is the new minimum, then we set the min set to be equal to item, and at the end we are going to return the min set. And everything should had been working perfectly fine, and the name find min connected set, we need to find min connected set. So there are not any more errors, and let's go inside Unity and let's see how that helped. So again, it is not going to be perfect, but what we can do is whenever it finds a new position, instead of randomly searching, so did my PC crash? Yeah, it crashed. So there are going to be bugs. The code is not yeah, the code is perfectly fine, but let's see what problems there were. So we'll fix the bugs in the next part and we'll see how it looks. So in the previous part there was a minor bug, and let's see how our game works currently right now. So instead of checking for too many solutions, we are just checking for only 100 solutions. And if we go to our 0 level, previously we were checking for around 20,000 solutions, and let's increase the speed. We don't need so small speed, we'll increase the speed to 16,000. And yeah, it is going to go pretty fast. And let's first fix our bug. So it was just one minor bug, so everything was fine, but previously there was point here. So instead of point, we will need to use the neighbor, because that neighbor needs to be contained in the all points, not the current point, because it will cause issues. And that's it, just this one variable, and our game crashed. So it is good to know that where was the issue. And let's go inside Unity and let's see how our game works with our 4x4 grid. So again, previously there were 20,000 solutions, so it is not going to change much, but again there are only 20,000 solutions, but the core is if we go inside 1x1 grid and we'll set the speed to just 1000 or around 800, then as you can see, so it is finding solutions pretty fast, so we won't be able to see it here. Let's increase the count again, and again it is finding the solutions pretty fast. So in around 1000 tries found the solution, and this are going to be problematic. So it is Which one was added last? So it is checking for this grids and it is modifying the previous, but as you can see, this grid was created way too far. So it was created at the start, so that's why it is not going to uh, get cleared. And again, that's some issue here. So when the all of this grids match are going to fail, then only it will go to this grid and then it is going to rearrange itself. So as you can see, it created problems, but not every time. It can almost find a solution in around 1000 tries, and we can find a solution pretty fast. So as you can see, it went till there. Yeah, so I think, yeah, it is not finding a solution pretty fast, so we need to forgot to add one more thing. So yeah. So we added our min set, but it is never getting used. That is one more bug. So I didn't add it because my game crashed and I was not able to check. And again, it is good to if you find the original final branch and you can check there. So what we need to check, if for our one empty, if minset dot contains, then only we are going to add our item, and also for our empty positions too. So that condition should be added so it won't go round and round. It should have been added before, but but my game crashed, so I was not able to add it before. And let's now see if it is again going through those stupid solutions, or our method has evolved. So as you can see, it is finding solutions pretty fast, and we can go through to cross through again and let's see what happens. So as you can see, it has again found the solutions pretty fast and again fast. And let's go to the 3 cross 3 grid, and it is always going to find the solutions faster till it reaches 5 cross 5. So yeah, so as you can see, within 1000 tries it reached a solution, so there is no issue for a 3 cross 3 grid. And again, it is going to get a solution in less than 1000 tries. It didn't happen here, but most of the time it will happen. So as you can see, within 1000 tries it's got a solution, and the number of solutions are pretty high, so we don't need to like check if the next solution is going to be pretty far. So there are almost like millions and millions of solutions for a 6 cross 6, and as you can see, the stupid solution here. So we'll need to create one more method. So instead of checking for empty positions whenever we are going to check for new positions, so when it reached here, this is going to create a pocket. So what we need to check, if whichever unreached pocket it has created when we created a new set, and also the minimum number of, yeah, so it doesn't matter. So that is going to be one more condition. So it is a stupid solution, but it won't be everywhere. We can just set a hard limit of 1000, and if we just go through it more times, we are always going to find a solution. So as you can see, there is going to be a solution here, and this is not going to have a solution because there is just one grid. Yeah, it will have, I think, but again it is going to create problems. But here in the third try we found a solution, and let's increase the size and let's see how it looks. So when it is going to end here, here, here. Yeah, that was because it was problematic here. And again, it is going to find more stupid solutions. So the main issue is when it finds a stupid solution, it always messes up. I don't know why that is happening because the ordering may be different and it should have, yeah, so it should have finished this loop earlier, but it didn't. And all the successive are messed up. And this is a 2 cross 2. So why did that happen? Because we prioritized a neighbor more. So we should prioritize a neighbor less. And again, it is finding solution, but it is not too problematic. And this should be a fine solution. This is also good, and this should have been fine, but I don't know. So yeah, so maybe, yeah, so there should be problem here. So as you can see, it just checked that here we cannot add anything, and that's why it is creating a problem. And let's now go through our 7 cross 7, and let's see, do we need to change anything? Yeah, this is a stupid solution, and I don't know when it is going to just pass through there. Maybe it will take a billion tries or maybe more, and we just need to cut off the solution when we find it. And as you can see, this is a good one. Are there any? Yeah, there is one stupid solution here. So it is the core problem with our method where we put the biasing for our min set, and it would have been problem because maybe it is having two multiple 3 cross 3 min sets. So as you can see, this is 3 cross 3 and this is 3 cross 3, but this one never got checked because it found like here it was impossible, so it is going to go through all of the solutions, so that is also going to be problematic. And again, because it is never going to find an empty position because it would have cleared everything, so that's why it is going to go through the neighbor. So our neighbor was not having any problems. And so why did this happen? I think it would be because of here. Where is the stupid solution which is telling it to? Okay, here. So why it is happening? Because the empty positions are here. And if we add any of the empty position here, then it should be cleared, but it is not selecting a new node, so that is problematic. If this would not have been created, it would not show such problems. And let's check for some larger grid size. So as you can see, there are always going to be stupid solutions and we can't do anything about it. We'll need to modify our current script, and yeah, we'll do that in the next part. So we'll fix that everything in the next part, and we'll see how we are going to fix it.